Welcome dear learners. We are continuing Unit 4 Fundamentals of Analytical Chemistry. In the present module we are discussing dichrometry. The contents of this module are K2Cr2O7, that is potassium dichromate as oxidizing agent, dichrometry, external and internal indicators, selected titrations using K2Cr2O7, equivalent weight calculations and problems based on these concepts. First of all, K2Cr2O7 as oxidizing agent. You are familiar with oxidizing agent and reducing agent. What is an oxidizing agent? An oxidizing agent is a material that will undergo reduction during a reaction. Oxidation is the process of increase in oxidation number or loss of electron. A reagent which is responsible for oxidation is termed as an oxidizing agent. In this part of the discussion, we are focusing on potassium dichromate, that is K2Cr2O7, and its performance as an oxidizing agent. Potassium dichromate or K2Cr2O7 is a common inorganic chemical reagent most commonly used as an oxidizing agent. It is an orange colored crystal as shown here. This potassium dichromate is a crystalline ionic solid with very bright red orange color as shown here. So, potassium dichromate is a crystalline solid which is bright red orange in color. It is also known as, this potassium dichromate is also known as potassium bichromate, bichromate of potash, etc. So, bichromate of potash or potassium bichromate are synonyms of potassium dichromate. Now, potassium dichromate is moderately soluble in cold water but easily soluble in hot water. It is not deliquescent. That is, potassium dichromate will not have the property of absorbing moisture from the air and just dissolve it. It is not associated with the deliquescent property or hygroscopic property. It can be used as a primary standard in volumetric analysis. You are familiar with the concept of primary standard. What is meant by a primary standard in volumetric analysis? In volumetric analysis, we must have a solution with exactly known concentration. That is, we must have a standard solution. A substance which is used for the preparation of such a standard solution is termed as the primary standard. The primary standard must be stable, it must be crystalline, the solution must be stable, it should be easily soluble in water, it should not be deliquescent, it should not be hygroscopic. There are several features associated with the primary standard. So, you have to remember the fact that potassium dichromate is a primary standard that can be used in volumetric analysis. Potassium dichromate fixed quantity can be weighed up with the help of some analytical balance. It can be transformed to some conical flask and made up to the mark, so you will get a solution with exactly known concentration. So, potassium dichromate is a standard, a primary standard material used in volumetric analysis. But remember, KMnO4, that is potassium permanganate, that we learned in the last module, cannot be considered as a primary standard. At the same time, another oxidizing agent, potassium dichromate, is a primary standard. Potassium dichromate as an oxidizing agent is the part of the discussion we are proceeding now. Potassium dichromate acts as a powerful oxidizing agent, especially in acid medium. Potassium permanganate can act as oxidizing agent in acid, base or neutral medium. Remember, potassium dichromate shows its powerful oxidizing tendency in acid medium. That is, potassium dichromate acts as a powerful oxidizing agent in acid medium. Now we can consider its reaction with the sulfuric acid. And this reaction is responsible for the oxidizing nature of potassium dichromate. The left hand side shows potassium dichromate and sulfuric acid. Here in this expression you can see a single molecule of potassium dichromate. It reacts with the 4 molecules of sulfuric acid. As a result of the reaction between these two reagents, you will get the products K2SO4, that is potassium sulfate, Cr2SO4 thrice, that is chromic sulfate, water and 3 nascent oxygen. Nascent oxygen is responsible for oxidation. So, as a result of the reaction between potassium dichromate and sulfuric acid, there occur the liberation of 3 nascent oxygen. These nascent oxygen responsible for several oxidation reactions. In the coming slide, we will discuss what are various type of common oxidation reactions shown by these acidified K2Cr2O7. So, remember, potassium dichromate, when mixed with the sulfuric acid, it can perform as a powerful oxidizing agent. And this is the reaction responsible for the oxidizing nature of potassium dichromate when it is mixed with the sulfuric acid, that is in an acid medium. Now, the oxygen liberated in this reaction can perform several oxidation reactions. And we are having some examples. Prior to entering into examples of oxidation reactions shown by acidified K2Cr2O7, we have to again recall the reaction responsible for the oxidizing nature of acidified KMnO4. That is the same reaction, K2Cr2O7 plus 4H2SO4 gives K2SO4 plus Cr2SO4 thrice plus H2O plus nascent oxygen. So, in this reaction, you have to consider one very important thing, that is nothing but we have to use the change in oxidation number as far as this reaction is concerned. Here, chromium is present in +6 oxidation state. So, in this case, chromium is present in +3 oxidation state. During the course of this reaction, +6 oxidation state is just reduced to +3 oxidation state. So, there is a decrease in oxidation number. Decrease in oxidation number means reduction. So, reduction occur for potassium dichromate. Reduction happen for an oxidizing agent. So, it is very well clear that potassium dichromate acts as an oxidizing agent in this reaction. In order to balance this equation completely, you have to put 4 water molecules here in order to get a very well balanced equation, because in this expression itself it is clear that the left hand side shows the 4H2. So, you have to put 4H2O to balance the number of hydrogen atoms. So, this is the exact equation. K2Cr2O7 plus 4H2SO4 gives K2SO4 plus Cr2SO4 thrice plus 4H2O plus 3 nascent oxygen. Now, we can have some examples of oxidation reactions shown by acidified potassium dichromate. This acidified potassium dichromate oxidizes acidified ferrous sulfate to ferric sulfate. Ferrous sulfate contains iron in 2+ oxidation state. It is oxidized by acidified potassium dichromate to ferric sulfate, and that is shown in this equation. 2FeSO4 plus H2SO4 plus 1 nascent oxygen. Here there are 3 nascent oxygens liberated, out of which only 1 oxygen is utilized in this reaction. So, 2FeSO4 plus H2SO4 plus nascent oxygen gives Fe2SO4 thrice plus water. So, it is clear that ferrous sulfate is oxidized to ferric sulfate by acidified potassium dichromate. Now, this acidified potassium dichromate oxidizes potassium iodide to iodine. This is the reaction responsible for this reaction. K2Cr2O7 plus 4H2SO4 gives K2SO4 plus Cr2SO4 thrice plus 4H2O plus 3 nascent oxygen. Here also you have to put 4 water. So, that oxygen convert potassium iodide to iodine. Look on the oxidation state of iodine here. Here iodine is present in -1 oxidation state. K plus and I minus is potassium iodide. That potassium iodide is converted to I2. In I2, iodine is in 0 oxidation state. So, there is an increase in oxidation number of iodine from -1 to 0. That is, oxidation happens to potassium iodide. The reagent responsible for that oxidation is acidified K2Cr2O7 itself. So, acidified K2Cr2O7 oxidizes potassium iodide to iodine. Now, this reagent, that is acidified potassium dichromate, can perform another oxidation reaction. That is nothing but it oxidizes hydrogen sulfide to sulfur. This is the reaction responsible for that oxidation. The first reaction shows the liberation of oxygen during the reaction between sulfuric acid and potassium dichromate to produce nascent oxygen, and that nascent oxygen oxidizes H2S to sulfur. Look on the oxidation state of sulfur here. Here sulfur is present in -2 oxidation state. That H2S is just converted to sulfur in 0 oxidation state. So no doubt H2S undergo oxidation to produce sulfur. This oxidation is performed by the oxidizing agent acidified potassium dichromate. That is, it is very well clear that it can oxidize, acidified potassium dichromate can oxidize H2S to sulfur. Now, another oxidation reaction shown by acidified potassium dichromate is here, that is, it oxidizes SO2 to H2SO4. SO2 is sulfur dioxide, H2SO4 is sulfuric acid. This simply means that acidified potassium dichromate can oxidize sulfur dioxide to sulfuric acid. This is the expression responsible for that oxidation reaction. The first one shows the liberation of nascent oxygen. There also, to get a balanced equation, you have to put 4H2 on the right hand side, that you have to keep in your mind. Now, that liberate oxygen, out of 3, you have to take 1, and that 1 nascent oxygen, this is exactly the nascent oxygen. This nascent oxygen oxidizes SO2, that is sulfur dioxide, to sulfuric acid. How you can show that this reaction is an oxidation reaction? For that, you have to take the oxidation state of sulfur on LHS and RHS. Now, we can take SO2 molecule. In SO2 molecule, the central atom sulfur is in +4 oxidation state, because oxygen is in -2 state. 2 oxygen atoms, -2 into 2, that is equal to -4, that is cancelled by +4 of sulfur. So, in SO2, sulfur is present in +4 oxidation state. That +4 state is converted to +6 state in sulfuric acid. In H2SO4, sulfur is in +6 oxidation state. So, during the course of the reaction, the +4 oxidation state of sulfur is just converted to +6 oxidation state. That is an oxidation reaction, and acidified KMnO4 is responsible for that oxidation. So, it is clear that acidified potassium dichromate acts as an oxidizing agent, or acidified potassium dichromate oxidizes SO2 to sulfuric acid. So, it is very well clear that there are several oxidation reactions shown by acidified potassium dichromate. There is one more example. This acidified potassium dichromate oxidizes sodium sulfite, that is Na2SO3 to sodium sulfate, as per this equation. Look on to the second reaction only. The first reaction is common in everywhere, and you have to put 4 water molecules to get a perfect balanced equation. And in that equation, it is clear that 3 nascent oxygen atoms are liberated by utilizing that oxygen. It is also possible to oxidize Na2SO3, that is sodium sulfide, to sodium sulfate. Na2SO3 plus this oxygen is the nascent oxygen, and the nascent oxygen convert Na2SO3 to Na2SO4. Last part I have to just put into 3. Into 3 is to get a fully balanced equation, that you need not to consider here, because in the first expression you will get 3 oxygen atoms as the product, out of which only 1 oxygen is consumed in this reaction. So, to get a balanced equation, you have to multiply the second equation with the 3 if needed. No need to balance it here itself. You have to understand the concept clearly, and the concept is this: Na2SO3, that is sodium sulfite, is oxidized to Na2SO4, that is sodium sulfate, by acidified potassium dichromate. Now, dichrometry. You are familiar with potassium dichromate, its nature as a powerful oxidizing agent, its various reactions depicting its oxidizing nature, etc. And now we are entering into dichrometry. You are familiar with the volumetric analysis. The volumetric analysis involving potassium dichromate is simply termed as the dichrometry, and now we can enter into details of the dichrometry. Dichrometry is a redox titration method that uses potassium dichromate, that is K2Cr2O7, as the titrant or as the oxidizing agent. It is one of the most common and convenient redox titrations due to strong oxidizing power of acidified potassium dichromate. You know, in permanganometry, you are using potassium permanganate as an oxidizing agent. That is due to its powerful oxidizing capability, especially in acid medium. Similarly, dichrometry utilizes potassium dichromate as an oxidizing agent. This is due to its capability as an oxidizing agent in acid medium. Now, in dichrometry, K2Cr2O7 acts as strong oxidizing agent, especially in acid medium. This point is very important. So, I just repeat this point. K2Cr2O7 is a powerful oxidizing agent in acid medium, especially in sulfuric acid medium. K2Cr2O7 is a primary standard in volumetric analysis. This point we made clear, and thus a standard solution of potassium dichromate can be prepared by weighing out a fixed quantity of potassium dichromate and can be used for further titration. That is, it is possible to prepare a standard solution, a solution with exactly known concentration of potassium dichromate, and you can use that standard solution of potassium dichromate to analyze the concentration of the given analyte. Now, dichrometry or titrations involving potassium dichromate, dilute sulfuric acid is preferred as the acid medium. During the reaction of K2Cr2O7, Cr plus 6 is reduced to Cr plus 3. This is here chromium is in plus 6 oxidation state, and here chromium is in plus 3 oxidation state. This is a reduction process. Reduction happens for the oxidizing agent, and K2Cr2O7 in acid medium is a powerful oxidizing agent. To get to the balanced equation, you have to put a 4 here, and this is the equation responsible for the oxidizing nature of potassium dichromate in acid medium. There are two types of indicators for dichrometry titrations. That is, in dichrometry or in titrations involving potassium dichromate as a titrant, we have to find out the end point, and to find out the end point, we need some indicators, and there are two kinds of such indicators. They are external indicator and internal indicator. As the name indicates, the internal indicator is mixed with the reagent. However, external indicators are placed outside the reaction medium. We can enter into more details of external and internal indicators in coming slides. External and internal indicators. In dichromate titrations or titrations in dichrometry, since potassium dichromate K2Cr2O7 is not a self-indicator, it is unlike KMnO4. KMnO4 is a self-indicator. We require both external and internal indicators. We can use either of this to find out the end point in dichrometry. That is, external and internal indicators can be used to detect the end point in dichromate titrations. Out of which we are discussing external indicators first. Potassium ferricyanide with the molecular formula K3FeCN 6 times. This is a coordination complex. Potassium hexacyanoferrate 3 is its IUPAC name. Here, iron is present in plus 3 oxidation state. This compound is used as external indicator in dichrometry. As the name indicates, this reagent, this external indicator should not be mixed with the reaction medium. That should be placed outside the reaction medium in some tiles, some porcelain tiles, etc. Now, it is preferably used for this reagent, potassium ferricyanide. It is preferably used for titrations involving Fe2 plus, that is ferrous ion with the potassium dichromate. Fe2 plus reacts with the ferricyanide ion or ferricyanide to form Turnbull's blue, which is a highly deep blue colored complex. This Turnbull's blue is the deep blue color whenever you are mixing Fe2 plus with the indicator potassium ferricyanide. Small drops of ferricyanide solution are placed on a white tile. This should not be mixed with the reaction medium because we are dealing with the external indicator. Potassium ferricyanide is an external indicator. During the titration, small drops from the reaction mixture are removed using a glass rod and spotted onto the indicator drops. As long as Fe2 plus ions are present, there occur the blue color or the blue color persists. But the end point is reached. When the end point is reached, no blue color forms on the spotting or during spotting, which indicate that complete oxidation of Fe2 plus to Fe3 plus occurs. This point I will make clear once again. Only Fe2 plus can form blue colored species, that is Turnbull's blue, when mixed with the potassium ferricyanide. If all the Fe2 plus ions are oxidized to Fe3 plus, there will be no more Fe2 plus ions and the color will be totally disappeared. That is the end point of the reaction. Now we are discussing the second category of indicator that we are using in potassium dichromate titrations. They are nothing but internal indicators. N-phenyl anthranoic acid, abbreviated as NPAA, NPAA, and diphenyl amine are two common internal indicators. As the name indicates, these materials can be mixed with the reaction medium similar to phenolphthalein, dimethyl orange, etc. So, these kind of indicators can be mixed with the reaction medium to get to the end point. This is the chemical structure of N-phenyl anthranoic acid, which is shown on left hand side, and diphenyl amine, which is shown on the right hand side. These two are organic molecules which can exhibit a specific coloration, and they are preferably used for the titrations involving Fe2 plus ions, ferrous ions with the potassium dichromate. Out of which we can take the first one in more detail, that is N-phenyl anthranoic acid is considered here. In reduced form, N-phenyl anthranoic acid is greenish or colorless in solution. In oxidized form, N-phenyl anthranoic acid turns a violet red or purple color. During the titration of Fe2 plus with the potassium dichromate, all Fe2 plus ion is oxidized to Fe3 plus in acid medium. As long as Fe2 plus is present, N-phenyl anthranoic acid remains in its reduced or colorless or pale green form. Once all Fe2 plus is consumed, excess of dichromate you are adding, and that excess, slight excess of dichromate oxidize NPAA. That is, NPAA is changed from reduced form to oxidized form. This indicate that, and this indicator in oxidized form produce a sharp color change, and that color change is from colorless or green to violet red. This is the method of action of N-phenyl anthranoic acid as an internal indicator. Now, the second internal indicator we are dealing with the dichromate titration is diphenyl amine. Diphenyl amine is colorless in reduced form and turn into intensively blue-violet, which is in oxidized form. During the titration with acidified K2Cr2O7, Fe2 plus is oxidized to Fe3 plus. The indicator is only oxidized after all Fe2 plus is consumed or oxidized. As the end point is reached, K2Cr2O7 oxidizes the indicator, giving a sudden blue-violet coloration. So, the formation of blue-violet coloration indicates the end point during the titration of Fe2 plus with the potassium dichromate. When diphenylamine is used as indicator, slight amount of phosphoric acid is also added. This is very important. Some syrupy phosphoric acid or small quantity of phosphoric acid is also added. This is to mask Fe3 plus ion, which would otherwise prematurely oxidize the indicator. So, if you are not adding the phosphoric acid during the titration, you will get a premature end point. So, in order to prevent that side reaction, you have to add a small amount of syrupy phosphoric acid. This is very, very important as far as diphenylamine internal indicator is concerned. Now we are discussing selected titrations using K2Cr2O7. First of all, estimation of ferrous ion or Fe2 plus ion. It is very well clear that Fe2 plus is easily oxidized to Fe3 plus by acidified potassium dichromate. So, the principle of this estimation is that acidified potassium dichromate oxidizes ferrous ion to ferric ion, which is given by this expression. Look onto the second expression, FeSO4 plus H2SO4 plus nascent oxygen gives Fe2SO4 thrice. This part we have already discussed. So, the oxidation of ferrous sulfate into ferric sulfate by acidified potassium dichromate is the principle behind the estimation of ferrous ion using dichrometric titrations. Now, the given potassium dichromate solution is standardized by using standard solution of more salt with N-phenylanthranilic acid as indicator. Standard K2Cr2O7 is titrated with given ferrous salt solution using N-phenylanthranilic acid indicator or diphenylamine as indicator. And these are the steps that we have to adopt during the estimation of the ferrous ion using dichromate titrations. First of all, you have to prepare a standard solution of more salt. The standard solution of more salt can be used to standardize the given K2Cr2O7. In certain cases, you can also directly weigh some amount of potassium dichromate to get a standard solution as such, because K2Cr2O7 as such is a primary standard. Otherwise, if some solution is given and its concentration is not known exactly, then you can take a more salt, a fixed quantity of more salt, and prepare a standard solution of more salt, and by using that more salt solution, you have to standardize K2Cr2O7 first. So, you go to standardized K2Cr2O7, and by using that standardized K2Cr2O7, you can estimate ferrous ion. So, these are the steps we generally adopt for the estimation of ferrous ion using potassium dichromate. Now, another example is estimation of ferric ion, Fe3 plus ion through dichromate titrations. It is very interesting to talk about the estimation of ferric ion. You have to remember the fact that potassium dichromate in acid medium is a powerful oxidizing agent. Iron is here present as Fe3 plus state, or iron is in ferric state. It cannot be further oxidized. Only Fe2 plus can be oxidized to Fe3 plus by using potassium dichromate. So, the question arises, how you can estimate ferric ion using potassium dichromate? For that, you have to convert ferric ion to ferrous ion first. Then you can estimate ferrous ion. The amount of the ferrous ion is also equivalent to amount of ferric ion present in the sample. That's why it is possible to estimate ferric ion. We can now enter into the details. Fe3 plus ion is reduced to Fe2 plus ion using stannous chloride solution. This is the first part of the experiment. So, the Fe3 plus given in the solution is reduced to Fe2 plus. Now, Fe2 plus is produced as the product, here essential to act as the reducing agent. In certain cases, some excess SnCl2 may also present. that you can remove by mixing with the mercury chloride HgCl2. Then the Fe3 plus in the given solution is converted to Fe2 plus quantitatively. Finally, acidified potassium dichromate is used to oxidize ferrous ion to ferric ion, and this is as per this equation. Ferric ion is produced as a result of oxidation of ferrous ion with acidified potassium dichromate. So, the principle of estimating ferric ion is that ferric ion cannot react with the potassium dichromate. So, first of all, it is reduced to ferrous ion by using SnCl2. Excess SnCl2 is removed by adding HgCl2. Now, all the Fe3 plus ions are converted to Fe2 plus ions, and then you can titrate that Fe2 plus ions with acidified KMnO4, acidified K2Cr2O7. So, this made possible the estimation of ferric ion. Now, the given potassium dichromate solution is standardized by using standard solution of more salt with N-phenylanthranilic acid as indicator. Standard K2Cr2O7 is titrated with the reduced ferric ion solution, that is ferrous ion solution, using N-phenylanthranilic acid as the indicator. These are the steps in consolidation. The first step is the preparation of the standard solution of more salt, which is for the standardization of potassium dichromate. And the second step is the standardization of K2Cr2O7. Third step is the reduction of Fe3 plus ion present in the given solution to ferrous ion. And the fourth step is the titration of the ferrous ion solution, that is reduced ferric ion solution to with the potassium dichromate to estimate the amount of ferrous ion, which is equivalent to amount of ferric ion present in the sample. Now, some equivalent weight calculations. Equivalent weight or equivalent mass is a very popular thing associated with the qualitative as well as the quantitative analysis is concerned. Equivalent weight is the mass of a substance that will react or displace a fixed quantity of another substance, such as 1.008 gram of hydrogen, 8 gram of oxygen, and 35.5 gram of chlorine. This is very important. That is nothing but equivalent weight of oxidizing agent and reducing agent. The equivalent weight of an oxidizing or reducing agent is the mass of the substance that can gain or lose 1 mole of electron during a redox reaction. This expression is used to calculate the equivalent weight of oxidizing and reducing agent. Equivalent weight is given by the expression molar mass or molecular mass of the substance divided by number of electrons transferred during the reaction or transferred per molecule during the reaction. The number of electrons transferred equal to total number of electrons gained for oxidizing agent or lost for reducing agent in a balanced redox reaction. Now, we are taking acidified potassium dichromate to calculate its equivalent weight. Molecular mass of or molar mass of potassium dichromate will be equal to 294 gram per mole. In acidic medium, Cr2O7 2 minus is reduced to Cr3 plus. So, 6 electrons are transferred during the process. So, number of electrons transferred will be equal to 6. And equivalent weight will be equal to molar mass divided by number of electrons transferred. So, that is 294 divided by 6, and equivalent weight will be 49 gram per equivalent. This value is very, very important as far as dichromate titrations are concerned. Equivalent weight of acidified potassium dichromate will be equal to 49 gram per equivalent. Now, equivalent weight of more salt. You know, more salt is a reducing agent. More salt is oxidized as per this equation. Ferrous sulfate present in more salt, that is ferrous sulfate, ammonia sulfate 6H2 is the more salt. The ferrous sulfate present in more salt is oxidized to ferric sulfate during its reaction with an oxidizing agent like acidified KMnO4 or acidified potassium dichromate, etc. So, in this transformation, it is clear that 2 molecules of more salt reacts with 2 equivalents of oxygen. So, the equivalent mass of more salt is same as its molecular mass. The molecular mass of more salt equal to 392, which is same as its equivalent mass. So, equivalent mass equal to molecular weight or molecular mass, that is equal to 392. It is very, very important to say that equivalent weight of more salt is 392. Equivalent weight of potassium dichromate in acid medium is equal to 49. etc. Now, as the last part of this module, we can have some problems based on the concept we learned. The first problem, how many grams of potassium dichromate are needed to prepare 100 ml 0.5 normal solution? This expression is very popular to you. Weight required can be calculated by using the expression VEN by 1000, where V represents the volume of the solution in ml, N represents the normality, and E represents the equivalent mass of the solute. And in the present problem, the material is potassium dichromate and its equivalent mass equal to 49. Volume is given in the problem, that is equal to 100 ml, and the concentration required is equal to 0.5. You have to substitute all this data in the expression Vn divided by 1000. You will get 100 into 49 into 0.5 divided by 1000, and the final value will be 2.45 gram. Thus, it is very well clear that whenever you are weighing out 2.45 gram of potassium dichromate and made up to 100 ml, you will get a solution of 0.5 normal concentration. Now, another problem, find the weight of more salt required to prepare 0.05 normal 250 ml solution. Again, you can use this expression, Vn divided by 1000, V represents volume, N represents the concentration or normality, and E represents the equivalent mass of the solute. Whenever you are making apt substitution, volume as 250 ml, equivalent weight as 49 because equivalent weight as 392 because you are dealing with the more salt, and normality as a 0.05, you will get the weight as weight required equal to 250 into 392 into 0.05 divided by 1000, that is 4.9 gram. This simply implies that 4.9 gram of more salt is weighed out, just made into a solution of 250 ml volume. The concentration will be 0.05 normal. Now, in a titration with the standard more salt in acid medium, the concentration of a solution of potassium dichromate is obtained as 0.51 normal. What is the weight per liter of potassium dichromate solution? It is very well clear that weight per liter can be calculated by using the expression weight per liter equal to normality into equivalent weight. Here in the problem, normality is given as 0.51, and for potassium dichromate, its equivalent weight is equal to 49. So, you have to multiply 0.51 with the 49 to get the result. That is 24.99 gram will be the weight per liter. Now, an MCQ based on the concept, the volume of 0.1 normal mole salt are required to neutralize 20 ml solution of 0.125 normal K2Cr2O7 in acid medium is. These are various options. Option A 20 ml, option B 25 ml, option C 10 ml, and option D 12.5 ml. You can simply use the expression N on V1 equal to N to V2. You have to find out the volume of more salt. So, V1 is unknown. N1 is equal to 0.1. So, you have to use 0.1 multiply with the V1 equal to 0.125, that is N2 multiply with the V2, V2 is equal to 20. So, in order to get to V1, you have to divide this quantity with the 0.1 and you will get the final answer as option B, that is 25 ml. This is the last problem. 4.9 gram of potassium dichromate is dissolved in 100 ml water to get a solution. The normality of the solution will be, these are the options, 0.01 normal, 1 normal, 0.5 normal, and 4.9 normal. It is very important to remember the expression normality equal to weight per liter divided by equivalent weight, and you have to find out the weight per liter. Weight per liter 4.9 gram is present in 100 ml. So, weight per liter is equal to, just multiply this with 1000 ml because 1000 ml is 1 liter. This will be the weight per liter. Weight per liter divided by equivalent weight. Equivalent weight is equal to 49. On simplification, you will get to the final answer as option B, that is 1 normal. That all about the present module, dichrometry. Have a nice learning experience. Thank you.